I welcome you to this class of econometric methods. Myself, Dr. Muhammad Imdadul Haq, an associate professor at the Department of Economics, Aligarh Muslim University. We, in our previous classes, discussed stationarity and how to measure stationarity. Now, we are going to the next step. That is, we will be looking at a phenomenon of cointegration. In economic terms, the economic implication is that if two variables are cointegrated, it means they have a long-term, or you can say a long-term relationship between them, or you can say they have a equilibrium between the variables, or there is a long-term relationship between the variables. We have seen before, we have discussed it before also, that if the data is not stationary, then the results could be spurious. We have also seen one of the rules, if you remember the discussion on the rules of integrated series, one of the rules was if yt and xt are I1 integrated of first order, then a linear combination of them will also be I1. A linear combination means a combination which we can make with using these two values. This was one of the characteristics of this integrated series. But there is a special case, and that special case is even if yt and xt are integrated at first order, there can be a case where a linear combination of them is not I1, rather I0. If that is the case, then we can do meaningful interpretation from these two non-stationary series. Now, before the advent of this method of cointegration, the practice was that we used to make the process stationary by differentiating. That is, we have with the process which we have repeated many a times. We have xt and then we take xt minus 1, that is we take one lag, and then we do xt minus 1. But this was the generally accepted practice. But if you are doing this, we are committing a very big mistake, and that is we are destroying all the long run properties. You have taken your resultant series is just a minus of one period over the last period. So you are losing all the long run characteristics from here. So, although the rule of integration, so that is the beauty of cointegration. The beauty of cointegration is, even if two series are non-stationary, if a linear combination of them is stationary, we can do the meaningful interpretation out of it. And we can say that these two series are having a long run relationship. That is how we are defining cointegration. Implies that the series xt and yt share similar stochastic trend, and since the difference term et is stationary, they never diverge too far from each other. So, as a general rule, to avoid the problem of spurious regression, non-stationary time series should not be used in regression. However, there is an exception to this rule, and that exception is if yt and xt are not stationary non-stationary at say I1 variable at I1 level, first order non-stationary, then we can expect their difference or any other linear combination like the one given over here, that is Et is equal to Yt minus beta 1 minus beta 2 xt as well. So to be I1, so this was one of the properties. If xt and yt are I1, their combination will also be I1. However, there is an important case where this Et is equal to Yt minus beta 1 minus beta 2 xt is stationary I0, then we can say that xt and yt are co-integrated. That is, they are moving together. They have a long run equilibrium relationship. To test whether xt and to test whether this xt and yt are are stationary or not, we can use that Dickey-Fuller test. We have this et hat. We don't have the exact et because we are taking a sample to study, so we estimate et hat. So if this series is stationary, there is a co-integration. If this series is not stationary, there is a spurious relationship. So natural way to test whether xt and yt are co-integrated is to test whether the error term is stationary or not. Since we cannot obtain Et, we test the stationary of the OLS residual, that is Et hat. Now, using a Dickey-Fuller test, the test for co-integration is effectively a test of stationarity of the residual. If the residual are stationary, then we can say that Yt and Xt are said to be co-integrated. If on the other hand, Xt and if Et is not stationary, then we say that Yt and Xt are not co-integrated, and any apparent regression, any apparent relationship between them is of spurious nature. So, see, the constructed I0 series works as a proxy of the power that drives the random walk and prohibits them to diverge. It is quite possible that two I1 series or integrated at first order series, or you can say the two series are having a stochastic trend, do share a common trend, so that a regression in one of them, a regression of one on the other will not be necessarily spurious. If you can recall an earlier example, which if you say a drunk man is walking in a very big lush green park, so he is moving like this. So from the looking, it looks that this series is not stationary, it's random, it's stochastic and all those things. But what the concern is, if that drunk person is having a pet dog with him and a leash is tied to the dog's neck and the drunk man is holding, so the dog will also move like along with him. Meaning thereby, even if one is moving in a stochastic, the other one is also following the same trend. Then we can say that these two series, say this is x and this is y, these two series are co-integrated. That is, they have a long run meaningful relationship between them. So the definition is, if the two series or more than two series under examination are integrated of the same order I1, and there is a linear combination of the series that produces a stationary I0 series, then the series is said to be co-integrated. So some of the condition is of the same order, the series should be integrated of the same order I1. So we can say that Yt is equal to theta 1 plus theta 2 xt plus Vt. Here xt and yt, they are I1, that is the two random variables. And if say theta 2 is equal to 0, that is they are not related if we regress yt on xt. So if theta 2 is 0, then we are left with only this one. Now, the properties of yt is the same. Now what is the case? The properties of yt is the same as the properties of vt. So because subtracting now according to the rule, subtracting a content from I1 will not alter its integrator properties. So Vt will also be Yt. So Vt we can write it as Yt minus theta 1. And again, so if the residual is I0, Yt and Xt are co-integrated. If the residual is I1, Yt and Xt are not co-integrated. So co-integration is this is a test of co-integration in the context of a single equation framework basically. Now we go by the estimation of Engel-Granger method and the steps involved in it. Now see, what we do, we assess the order of co-integration using any Dickey-Fuller test or any other. So xt and yt we check are I1. So xt and yt should be balanced in their time series, that is both of them xt and yt should be I1. So how to test it? We test it by, we have seen the process of testing the stationarity of the series. We check the stationarity of the series and we see that series X is all integrated, it was not stationary at level, and when we took the first difference the series was stationary. Same thing happened with Y series. The Y series what is not stationary at level, then when we took the first difference Yt also became stationary. Now then we will get the Vt, we will get the error term, and we will do OLS between xt and yt in this Engel-Granger process. We will do because we are basically discussing the single equation Engel-Granger process. Now we will do the regression and then we get the values of the error term, and using that error term, if you see now this error term, we put this error term in for the stationarity check, and if it is I1 means the error term is not stationary at level, but what happens, it is stationary at any other difference, but it is not stationary at level, then what we can say that the regression, that there is no co-integrating or no long run relationship between them. So we test the for stationarity on this Vt hat, and then we interpret whether there is co-integration or no co-integration. So when we do this test, we get Vt hat is equal to theta 1 Vt minus 1 plus epsilon t, and if the value of this theta 1 is less than 1, then there is co-integration. If this value of theta 1 is equal to 1, there is no co-integration. So gamma, you can, as we have seen before also, gamma we can say theta minus 1, gamma, if gamma is equal to 0, then it is a case of no co-integration. If gamma is less than 0, it means there was the basic the one thing, because we have seen before that if you use the Dickey-Fuller test, the element of autocorrelation could be present. So we need to check for autocorrelation, or what we do the alternate method. We do the alternate method of augmented Dickey-Fuller test. The equation is modified as we have seen in the previous cases. Now in ADF we can do no intercept with intercept and trend, but here we have only one model, that is Vt is a zero mean process, a random walk process. Vt is a zero mean process as it has no trend or intercept. So we do the basic tau statistics, we calculate the basic tau statistics, not the one with the drift, and slope, the trend value. So here the regression has no constant term because the mean of the regression residual is 0, and the critical values for this was also given by Engel and Granger. So this was the very very first process of cointegration as given by Engel and Granger. But there are certain issues with this Engel and Granger process. Nevertheless, it was a path-breaking and innovative method which was developed because these people, Engel and Granger and Weiss, they defined or they identified that these stochastic processes, this trend, it has an stochastic process, and you cannot use regression with these stochastic process. So you need to, they devised a method to deal with a stochastic process and derive meaningful conclusion, but provided there is a condition that when a linear combination of two I1 series is I0. Now, one of the issues is in cointegration, we treat the status of variable as same. We do not say that x is independent, y is dependent, or y is independent, x is dependent. We do not say things like that. So, but when you are doing the cointegration, you have to, or when you are doing regression, you have to identify, we have to put that this is x and x is independent and this is y and y is dependent. You have to do it. But suppose when we are taking one time, and what we are talking about cointegration, that is two series are moving together. So it is immaterial whether x depends on y or y depends on x. Now, xt, or in the example of our dog and drunk man, both of them, don't have a destined, the dog is not a trained police dog that it is going to do something, and that the man is not in a senses that he is going in a particular direction. Both of them don't have a sense of going to a particular location. They are just taking a stroll like this. So if you are taking y to be the dependent variable, and so Vt is the error term, suppose Vt is fine. Later on when we test this Vt, and this Vt is free from, it is I0 process. But again, next time say we take xt as the dependent variable and here yt as your independent variable and wt is the error, but say wt, it may be I1. Here till this case it is fine, but the moment we change the dependent and independent interchange between them, we get an error term, and once that error term was of the same two variables, once the error term was I0, next time the error term is I1. And this type of things can happen if the sample size is small. These things can happen. And this, if there are more than two variables, say maybe 3 or 4, again in 3 they are taking 4 variables, in 3 equations everything is fine, in the 4th equation there is a problem. So Engel Granger, it was a path-breaking, innovative thing, but it has its limitation in this scheme. It is a single equation framework, but still it has its own limitations. Second, if there are there are two variables, there will be one cointegrating relationship, agreed. But if there are more than two variables, then there may be, if there are 3 cointegrating variables, then there may be 2 cointegrating relationships. If there are 3 variables present, there may be 2 cointegrating relationships. So in Engel Granger, we do not know if there is one or more cointegrating relationship. We are not aware, we cannot identify from Engel and Granger whether there is one cointegrating relationship or 2 cointegrating relationship. Third, if yt and xt are cointegrated, it does not mean that they are moving in a straight line. We should be very clear. It's not that it's a linear, 2 regression lines can be drawn. But there may be a movement. What does this movement says? That there can be some other shape. So if xt and yt are together in the long run, short run, if there will be some short run deviations, but these short run deviations, they will correct themselves. Means you are going and then you have deviated and then you come back. The other series also, so it is, suppose it is going like this. It can be the case that one series has gone like this and other is straight. But what is the issue? What is the good thing is, and at this point the series is coming back to the same type of relationship. In Engel and Granger, we do not know whether xt is adjusting or yt is adjusting. So, means Engel Granger, this is not basically a limitation of Engel Granger, but once after doing finding the co-integration, the next thing which we have to do is to estimate the error correction model. We will study the error correction model in our upcoming classes. So, we have Engel Granger is not completely giving the correct picture. We have to estimate other things also. Now, once we have seen the process of Engel Granger and all, now let us see, we have a practical feel how this is done, how Engel Granger testing process is done. Nowadays, in softwares, you will not find Engel and Granger. The reason, this is for a single equation, it has a very strong, because normally you don't have only bivariate relationship of x and y. Now you have n number of independent variables, 5, 6, 7. In those cases, interpretation of Engel Granger, it becomes complicated. So nowadays, what's commonly seen is Johansson co-integration. Now, in order to have a feel of this Engel Granger, we will do it in bits and pieces using software and Excel sheet. So let us see. We have a series of y. We have a series of y, we have a series of x. We have these two series. Our data is there in Excel. Now, we are importing this data, so we go to open, then we go to foreign data as a work file. There are many ways. This is one of the most commonly ways, because we love our Excel, and we put the data in Excel and then we import to eViews. So we go for open, and then we foreign data as a work file, and then you select the Excel sheet. A dialog box will open up and it will show that the data is there in the system. Here you click next and then finish. So now you will find your data x and y is present in your eViews. Now you go to quick. Once you go to quick, now there are so many options and you have to select estimate equation. Once you go to select estimate equation, then you have many methods over here. If you can drop down, a full range of methods will open, but we basically need the least squares. Once you have selected least squares, then what we do, we write the dependent variable first, then we write C for constant. This C is just for constant, and then we identify one of the variables as independent, and that is x we write as independent. There are 55 observations that is being shown, and so then we click on OK. So we write the dependent variable first, and although independent and dependent doesn't have a lot of meaningful interpretation in terms of co-integration, but nevertheless we have to specify the software that one of them is dependent and the other of them is independent. So then we move on with OK. Once we do OK, we get the estimates. This is your intercept term. This is your intercept, and that is your alpha, and this is your beta. Your alpha and beta are there, and if you want to check the significance, since it is less than 0.05, it is significant. And there are other things, R square and all those things, we don't need it at the moment. Now, from here you got the value of alpha as minus 12.58, and for beta it is 9.83. Now, in order to just do it in a more simple way, we go in Excel sheet. Earlier we had our data y and x. Now we calculate y hat. Y hat is equal to alpha hat plus beta hat x. Your alpha hat was 12.58 and beta was minus 12.58 and beta was 9.83. What we have just now seen from here we are taking these two things. Now, once we have done this, then we get the value of y hat. Now, one step is missing. Once we have in that Excel sheet only, once we had got y hat, then we calculate y minus y hat. Here is your y and here is your column for y hat. We have a column for y hat, so we do y hat, we have a column. Then next time what we do, we calculate y minus y hat. This is nothing but your ET. Y minus y hat is nothing but your error term. Then what you do, suppose your error term was like this. I am just giving a hypothetical picture. It's not a correct thing. Say it is 2, 4, 5, 10, 12. Then you do another step, ET minus 1. When you do another step, this 2 it comes here, this 4 comes here, this 5 comes here, and this 10 it comes here. Now you estimate the equation as ET is equal to, say, any coefficient beta et or theta ET minus 1 plus VT. We are going to estimate this equation. So upon estimating this equation, we get ET hat. When we get this ET hat, now by using the same process which we are saying just now, we get a value of ET hat. This is nothing but we get a value of estimated ET. This is my estimated ET hat, the column, and this is my ET hat with a lag 1. So this is nothing but this one is y hat, this one is ET hat, and this is ET minus 1 hat. So now we have done the regression, we got the values of ET hat, we put it, now my software is having the value, and then next what we do, we again go to our old technique of estimating stationarity. Augmented Dickey-Fuller, we take first level, we take the first case only, the intercept case. It is not significant, but remember, do we need to take this? If you recall your discussion, we should not be taking the case with the drift. No, we will not take this case. In this case, drift and trend, we have told that we will not take this case also, and here also the probability says that it is not stationary, but we will not take this case. Because we have been told over there in our discussions on that we should take a case in which it is selected at level, and we will take the none, no trend, no intercept. Now when we do this case, we see that our p-value is 0.03, 0.05, p-value is less than 0.03. It means the process is stationary. So now what we have proved? We have proved that although we got that we assume that xt, the variable xt was in such a case that it is I1, yt is I1, agreed, but we got a linear combination of them in terms of ET, and this ET hat, this linear combination was stationary at level. Since a linear combination of an integrated series is stationary at level, we can say that these two variables are moving together, or we can say that there is a long run relationship, or we can say that there is a co-integration between yt and xt. But we have done this by the process of Engel and Grandcha. With this I end. This few slides means they should have been before. This is just showing how you have estimated my ET, the one which we had drawn by hand on the Excel sheet. So we have taken this estimation and then we have estimated this. Also we can see this value, see ET hat is equal to theta 1 ET minus 1 plus VT, and we see that this value is 0.92. If we remember theta 1, if it is equal to 1, non-stationary. If theta 1 is less than 1, it is stationary. Now see, it is 0.92, it is less than 1, and we can say that there is a relation, there is a co-integrating relationship between the two things. So, I hope this slide is also clear to you, wherein we have proved that theta is less than 1. We have taken we have done the regression between et hat and we have done the regression between et hat and et minus 1. And the necessary condition is theta 1. The value of it, this value should be less than 1. So, I hope the process of Engel grandeur is clear to you, although it is no longer put into use, but nevertheless it is the foundation stone of cointegration which is used to estimate relationship in time series data. Hope today's lecture was clear to you. Thank you.